So in this lecture, we're going to talk about the stress life approach to fatigue. And the stress life approach is a traditional design approach to metal fatigue, particularly for ferrous alloy steels. We can identify something called an endurance limit. And we'll talk about these different things pretty soon. But as we saw in the first lecture for the course, that August Wöhler was the one who kind of initiated the systematic approach to determining what was going on. There's some information on our box folder, and I'll bring up maybe a couple slides here. So there is August Wöhler, obviously in his later years. And here is a little blurb on him as written a number of years ago. So I don't know if I can zoom in on that or not. But I would encourage you to read through this. And one of the things I think is always kind of interesting is the advances in fatigue analysis also follow the advances in technology in general. So at the time where train axles were important, Wöhler designed his testing system to kind of mimic what was going on with a train axle. Later on, as we'll see, the stress life approach was used for a number of years. And then finally, something called the strain life approach to fatigue began to be developed. It was based on the ability to control servo-hydraulic testing machines very precisely in either load displacement or strain control, and in particular strain control for the strain life approach to fatigue. The ability to do that was only possible with the invention of microcomputers and that kind of technology. So things kind of keep pace with the general historical trend. So as we look at this data, we always have to think of the time period that this data was collected in and what was of interest to the researchers at that time. So one of the papers, again on our box folder, is Wöhler's book. And let's see if I can find a couple good pages for us to take a look at in here. Okay, so here's one interesting page I just ran across. In here, it's looking at notched bars, okay, and he's tracing the crack pattern around the notch where it initiated and how it separated. Okay, so he has a very sharp notch angle right here. It looks like something around 45 degrees. Again, this is all in German, so obviously don't expect anyone who can't read German to read through it. But it's interesting, some of the pictures that are in here. Let's see if I can find some more. Here are the tables of fatigue life that he has. So this number is a stress value. It's not exactly what we would use for the same units for stress today, but it is a stress value. So here's a stress and a corresponding fatigue life. And as we mentioned in discussing homework number 1 a little bit already, if the specimen never fails, then you don't have a number to put down here. So that's what this dash represents. So there's some certain level of stress at which this particular steel component didn't fail. Stahl for steel, Eisen is iron. And so, again, without reading all the details, you can tell by the pictures that he looked at shafts of various geometries and design. And again, this was his apparatus, so the specimen is in between, and there's kind of a spindle here, and some weight pans to carry the weight. And these adjustable lever arms and so forth, so that he could apply different types of loads and whatnot, and fairly precisely. Okay, so some really interesting detail in this. the level of mechanical precision in all of this, I think, is just amazing, and in some ways it's kind of lost to time, in that we can do many of the same things, but maybe so much more easily that it doesn't require the level of mechanical design expertise anymore for the typical user of a fatigue testing machine these days as what it would have required back at that time. My understanding is that these fatigue machines are still available to be examined in Germany in a museum. Of course, Prussia at the time is now part of modern-day Germany. All right, so one of the things that Wöhler didn't do, at least I didn't see it in any of his papers, was he never really made what we call the stress life chart. Okay? So he had all these tables of data, and he said, okay, if you test it under this stress level, then we don't think it's going to break. But he didn't show the chart. And so for your homework, what I'm asking you to do is to plot on log paper the stress amplitude and the number of cycles to failure or rupture. Okay, as we talked about previously, we have our round bar and it's rotating around. We use our stress formula for 4-point bending. Pure bending, we have sigma is equal to my over I. M is the bending moment. I is the moment of inertia. Those things are constant for a constant cross-section. But the distance y changes as we go and rotate a particular point around this bar. And as we saw from the previous lecture, we can, if we know the rotational frequency, then we can have this be proportional to something that looks like sine omega t, where omega is the rotational frequency of the bar. So we get a sine wave. Again, we talked about this last time, but we get a cyclical wave of stress at any particular point that takes it from tension to compression and back and forth until it breaks. We talked about some different terminology associated with it, and we said that from the mean stress to the top of the peak of this constant amplitude sine wave, we call this the amplitude. And that's what this term is here. So sigma amp for the amplitude, it means the same thing as SA. Now the reason why we're going to use the symbol S is to emphasize the fact that this formula that we used, sigma is equal to my over I, is related to a theoretical calculation from mechanics of materials based on elastic material behavior. All right, so if you're at low loads, certainly below the yield stress, that's a perfectly fine way to calculate stress. Although we've talked about we do have some damage that accumulates, so locally you might have some plasticity going on at these intrusions and extrusions, some permanent deformation. But from the overall perspective, the system is elastic. However, even in situations in which this stress calculated by linear elastic mechanics materials exceeds the yield stress, we're still just going to use this way to calculate it. We're still going to just say sigma is equal to my over I. We're going to ignore what happens when we're above the yield stress. And again, to emphasize that, we're using this term S sub A for the stress amplitude. So we'll make a little sub note here. This will be item A, our basic SN curve. All right, and so what I want you to do then is to plot on log paper the stress versus the number of cycles to failure. So as we talked about in the paperclip lecture, high stress amplitudes, short lives. And for some of Wooler's data, he gives a stress amplitude, but he didn't really list a number of cycles. Okay, so maybe he would say it lasted at least this long. When you come across this kind of data, and you may not be able to plot this depending on what information is given in Wooler's paper, we'll have to take a look later. But if you know the stress amplitude, but you don't know the number of cycles to failure, what you're going to have to do is you're going to have to show what you reached for the number of cycles to failure, and you're going to indicate that as a run out with an arrow on it. So how do you do this? Well, if you're plotting this by hand, you just take your pencil and put an arrow on that data point. If you use Excel, do the same thing. But these runouts are very important to indicate on your plot because that can influence the overall fit of the data. So for example, one of the things I want you to do then is I want you to fit a straight line curve, a best fit straight line curve of the data excluding the runouts. I'll switch to colors here. So if I were to look at this data and all these things failed, and we know that there's some variability in it, but maybe I could have a fit through that data up until that point that looks about like that. And one of the things that we notice with the SN curve is that for this range of loading that we'll talk about, where linear elastic assumptions, even if they're not strictly valid, are still pretty good, the fatigue life tends to plot as a straight line on a log-log curve. There's a saying that for engineers, happiness is a straight line on a log-log plot. Okay, so we're going to put here that for the SN curve, the data represents results of rotating bending tests for materials. Now, in particular, Wooler was looking at steel, but we can do the same kind of plot for aluminum, titanium, and so forth. If we look at the application that Wooler was looking at, train axles, he really wasn't interested in anything that didn't last very long. I mean, if you have a train and your train axle only lasts 1,000 cycles, that doesn't do anybody any good. So we're going to put some limits on this curve for the SN curve of approximately 10 to the 3 cycles. And typically what is often seen, and don't take this number to be a hard number, but if we use 1,000,000 cycles or 10 to the 6 cycles, we tend to see, at least in steels, this kind of bending over of the curve. So maybe there's a data point where it goes like this, and maybe they tested it for a long time, but it didn't fail, so it goes like that. And so if we were to kind of show this representatively on this plot, this red line would go flat at this point, indicating whatever stress level you were below this particular stress level, we would not have any fatigue failure. So let's take a look at some features of our best fit SN curve. Okay, so we have the data points and then we have the best fit curve, and that's what we talk about, the SN curve. And I'm going to represent this schematically. And again, the stress amplitude, and then over here the log of the number of cycles to failure. I'm going to have you plot Wooler's data so that you can make one of these plots on your own. Be careful if you haven't used log-log data log plots in quite a while. There's some can take a little bit of practice to make sure that you have the points line up in the right spots. Now, schematically, without drawing the data points on this curve, what we'll often see is a sloped portion, and then under certain conditions we can find this endurance limit value right here. Okay, so that's probably the most notable point that you'd see is SE. And this endurance limit, again, this is not a hard and fast number, but kind of a rule of thumb number, is it's around 1,000,000 cycles. So I'll often put 10 to the 6 right here. Again, if you have test data that indicates that that number is not 10 to the 6, then use the test data. But if you don't know anything else, around 1,000,000 cycles is often taken as the endurance limit for ferrous metals. In other words, steel. It's not seen very often in aluminums, titaniums, things like that. And we'll talk about some of these features, but it comes down to the makeup of the material, the number of active slip systems that can be involved. So our definition for the endurance limit is stress level below which the steel does not sustain fatigue damage. So if you were trying to design something for an infinite life, this is a pretty nice design point. You design to the endurance limit, and then you're pretty sure, if you've calculated your stresses right and accounted for certain things that we'll account for later, that your fatigue life should be a long time. Alright, so the endurance limit then is around 10 to the 6 cycles. And the left side of the graph, I'm showing this at starting at 10 to the 3 cycles. Okay, so less than 10 to the 3 cycles, we're in a range where there's a significant amount of plasticity. And typically when we use the SN approach, we're not interested in that much plasticity. We may have some finite life in between 10 to the 3 and 10 to the 6 that we might be interested in, and we're often usually very interested in what goes on at the endurance limit, but not so much interested left of 10 to the 3 cycles. Now the reason for the endurance limit that we see in ferrous metals as opposed to things like aluminums and titaniums is because the steels have certain features in them with their slip systems and their crystalline structure. They tend to be more body-centered cubic type materials, that they don't have as many active slip systems that can cause damage as opposed to face-centered cubic structures that you might see in aluminum. Again, emphasizing the importance of the microstructure on what happens to the fatigue life. Now this idea of resistance to deformation due to these slip systems having a harder time moving around and dislocations moving is also related to a material property called hardness. And again, this is for steels. Now there's different ways to take hardness measurements. But in this time period, we're talking about the late 1800s up until 1950s or so, a typical way to take hardness would be something with called the Brinell hardness number. We're going to abbreviate that as BHN. And in this test, you take basically a small ball bearing. It looks like a steel marble. It's very hard itself. And you give it a weight and you press it into your steel. And then you measure the size of the indent that is made. If you have this ball bearing on a soft steel, then you'll make a huge kind of crater. If you have a very hard material, then the crater will be smaller. And by looking at it through a graduated microscope type device, you would see that this Brinell hardness number can be determined. Now again, for steels, based on some data, and I'll show you the charts in just a little bit, the endurance limit can be estimated to be about 1/4 of the Brinell hardness number. Okay, so this is a purely empirical observation, and as long as your Brinell hardness number is around 400 or less. Now, if you go and do some of your own tests and you measure your Brinell hardness number, and this relationship is, BHN divided by 3.5, well, that's great. Use your endurance limit. In many cases, the hardest thing about engineering design is finding the material properties you're going to use in your design. We know how to do all this sophisticated stress analysis now, but we often don't have all the material properties that we would like to have. We know that these material properties are important, so many times it depends on us having some way to estimate these various material properties. Another rule of thumb that you may have heard of already through the Brinell hardness test is that the ultimate stress of a material is approximately the Brinell hardness number divided by 2. Again, this is for steels. Now, what is the ultimate stress? Well, if we were to do a stress strain test for our material, we would have a linear elastic range, we would yield, we would hit a peak, and we would come down. The ultimate stress would be the highest point on the engineering stress strain curve. And so here's kind of a plot that shows the basis of that relationship. Now, this plot takes just a moment to explain. What they've done in this plot is they've taken the stress amplitude that's on this axis, again you see it's a log-log type plot, and they've divided it by the ultimate strength. Okay, so this is SA divided by SU. Okay, so it's a normalized value. The highest you would ever expect would be to get to 1 on this vertical axis. And here's 10 to the 3, and 10 to the 4, 10 to the 5, 10 to the 6. And here's some interesting things to point out. So by normalizing it, then the endurance limit should be about half of the ultimate strength. Now, how well does that work? Well, it looks like it seems to work pretty well for these steels. Here we have 56 KSI steel all the way up to 190 KSI steel. We have some runouts down here. Now there's some failures, maybe a stress level just a little bit higher than this square right here. But if we just got a little bit lower, it looks like it's a runout. So that's around, maybe 0.52. Okay, we have some other cases here. We had a failure here, and we have some runouts here. So maybe that is around 0.46 or 48. Okay, so this 0.5, this half of the ultimate stress for the endurance limit, it's not something that don't take it as an absolute rule. But if you don't know anything else, if you don't have any other fatigue data to rely on, then we can use this as a rule of thumb. All right, well, let's talk a little bit more about this normalized curve. And there's a couple points that I want to, that are kind of significance. One of them is where this intercepts this curve here, and the other is here. Okay, so I'm going to show these positions on a little plot. Alright, so again with our normalized log-log plot, the stress axis being normalized, 10 to the 3, as we saw on the previous page, corresponds to about 0.9 times the ultimate stress. Again, this is our idealized curve. I keep emphasizing that, but I emphasize that for a good reason. And if we go to 10 to the 6, our approximate endurance limit, 1,000,000 cycles, this is approximately 0.5 times the ultimate stress. Well, we can fit this to a curve, a straight line on a log-log plot. This is a power relationship. The equation for this relationship in between 10 to the 3 and 10 to the 6, that equation would look something like S is equal to 10 to the C n to the B. Number of cycles to failure to the B. So we have two material constants that we can find. And we can calculate the B and the C for those, for this idealized curve. And if we do that, then we get the relationship, again emphasizing the approximate nature of this, 1.62 times the ultimate stress times n to the minus 0.85. Excuse me, 0.085. Okay, so that exponent is negative because the line slopes downward. And this rule of thumb, you can get an idea of how steep that slope is by the value of that exponent. Again, your equation may vary if you have data points. Now there's an awful lot of historical data, but again, you may want to be cautious about using that historical data until you have a really good idea of how that data was taken, collected, and what the surface conditions of that material were. These may or may not be suitable for your purposes. Oftentimes in these rotating bending fatigue tests, you'll go through and you'll polish your sample so that it has a mirror finish, so that you get the best possible fatigue life for that material. In other instances, you may have what we call an as-machined surface or an as-cast surface, in which case the surface may be a lot rougher than this mirror polish. But we'll see there are different ways to account for this kind of surface effect on your baseline data. Well, while we're here and before we get too far along, let's talk a little bit about what SN curves for non-ferrous alloys may look like. Alright, so SN curves for non-ferrous alloys, we're still talking about metals, typically don't have an endurance limit, although some people may define what they call a pseudo endurance limit of around 1 million cycles, kind of consistent with what we see for steels. The shape of this may look a little bit different as we curve down here. We just keep kind of coming down. We may never really approach a true endurance limit like we see in these ferrous alloys. So these would be things like aluminum, titanium. These are the most common engineering alloys that you'll see, although other materials can exhibit the same kind of behavior as well. Alright, so why have what we call a pseudo endurance limit? Why do we just not test everything until everything breaks? So we need to think about what goes on in our fatigue test. Suppose we have a test that we can run at 30 hertz. In my lab, for my testing machines, for the specimens that I test, 30 hertz is a really good test rate. That would be tension or maybe tension compression type loading. Oftentimes I can't test that fast, but maybe I could do 10 hertz or 5 hertz. Really complicated tests where we're looking at multi-axial fatigue, I might only be able to reliably test a half a hertz in order to get some data. But let's think about this. So 30 cycles per second, what is that, 3,600 per minute. So if we were in a Wooler bending fatigue test, we would be able to test this at, if we were able to do 30 hertz in there, that would be equivalent to 3,600 RPM. That's a pretty good speed for something as big as a locomotive or train axle. Let's think of what that corresponds to in the amount of time to complete a test. If we say the endurance limit is 1 million cycles, that's 10 to the 6. We want to calculate the amount of time that it takes at 30 cycles per second. 60 cycles, 30 cycles per second, 60 cycles per minute. I think I did my calculation wrong there when I said 3,600. Let's see what that is per minute. It's 1,800 per minute. And if we do per hour, I'm going to multiply it by another 60. That's 108,000 per hour. So if we did 1 million cycles, and we divide it by 108,000, I get 9.25 hours. So let's just call it 9.5 hours. It takes you a little bit of time to get the test set up. Alright, so you come in the morning, you start your test, and if you do 30 hertz, by the end of the day, a long day, an engineer's day, you get 9.5 hours and you get to 1 million cycles. So that's not bad. But let's say you really wanted to see if the endurance limit was real. Okay? So instead of testing at 10 to the 6, maybe you keep testing until you get to 10 to the 7 cycles. Well, now that 9.5 hours turns into 4 days. All right, well, you come in on Monday and it's done before you leave on Friday. Okay, you can live with that. What if you didn't think that 10 million was enough cycles? You really wanted to, really wanted to get a long life test, 10 to the 8th cycles. Well, it's 10 times longer. All right, so you come in on January and you're done by the middle of February. That's a pretty long test. A lot of things can go wrong in 40 days of continuous testing. The power may go out, the temperature may fluctuate in certain ways as to cause expansion of your test article in your apparatus, and you may throw your stress levels off. Different things can happen. And if we extend this, then of course 10 to the 9th cycles, 400 days, we'll just put more than 1 year. That's pretty much impossible. Now Wooler did some very, very long fatigue tests to get some of his data. I don't know the frequency that he used. If one of my students out there can take a look in his paper and decipher his testing frequency, that would be something kind of interesting to know. But again, 30 hertz is a pretty good test rate. If you can't do 30 hertz, then you're just adding on. If you can only do 10 hertz, you have to multiply all these numbers by 3. So tests more than 10 to the 8th are very rarely done in the fatigue testing community, unless you have some very special equipment. We're talking about something like a vibroacoustic testing machine, and they do make some of those, and I've seen some of those in operation, but they're very special pieces of equipment. Usually the specimens are very kind of small, kind of dainty. You really have to know what you're doing with those, and you have to be careful and see what you can do. Of course, the real trick is to get this vibrating in the area of kilohertz or megahertz even to try to do this fatigue testing. And then you have all kinds of other potential issues with heat dissipation and so forth that you might have. But there is some high-speed fatigue testing equipment. We do not have that currently at the University of Alabama. All right, so in this lecture, I spent a little bit of time kind of introducing you to the stress life approach. The traditional stress life approach is with rotating bending testing with a zero mean stress. However, there are a lot of important situations where we might not have a zero mean stress. So in the next lecture, we'll spend a little bit of time talking about mean stress effects and other things that can influence our standard stress life curve.